Good evening. Welcome to Krishna's classroom. In the last lecture, we introduced the concepts of total boundedness and epsilon net. And the problems that we looked at afterwards clearly indicated that they have a role to play in the structure of compact sets. And we make a few observations that we have already seen, namely that we have seen that in R a compact interval of 0, 1 is which is closed and bounded. In fact, all closed bounded subintervals of R are compact. However, this is not something valid in all metric spaces. We have already seen enough number of examples. Then we examined this carefully and we found that 0, 1 is totally bounded. So naturally the question is, does it mean total boundedness implies compactness and vice versa? The answer is no. Because we have seen the open interval 0, 1 is totally bounded. This is also totally bounded. In fact, every subset of this closed bounded interval 0, 1 is totally bounded. Therefore, total boundedness alone does not imply compactness. But on the other hand, found that the difference between the open interval 0, 1 and the closed bounded interval 0, 1 is that 0 and 1 are included. And what is the status of 0 and 1? The points 0 and 1 are limit points of 0, 1 of the open interval 0, 1, which do not belong to this set. Okay. Therefore, you see that suppose those points also are included, would you get compactness? In fact, one of the essential features of this compact interval 0, 1 is that it is complete, whereas this is not complete. So possibly total boundedness along with completeness would assure us compactness. Okay? So we proceed in this kind of with this kind of intuitive feeling. First, we prove that if a space is compact, then it is not only totally bounded but also complete. So the question that you ask is this: total boundedness and plus completeness. When it appears on the examples, this is true. So let us explore this. So what we want to explore first is this question. Okay. Because already we are convinced that total boundedness alone does not guarantee compactness, and from the structure of R, which is complete, but it's not totally bounded. Therefore, one of these two properties alone cannot assure you compactness. So our objective is essentially to prove the equivalence of the two, but then, as I suggested in the beginning, our strategy is the first statement, X compact is equivalent to X totally bounded and complete. That is equivalent to every infinite subset of X as a cluster point, and that is equivalent to every subsequence in X has a convergent subsequence. The strategy is, of course, 1 implies 2, 2 implies 3, 3 implies 4, and 4 implies 1. So cyclically we prove this because implied is a transitive relation. It would, from this you get that any one of them is equivalent to any other of these 1, 2, 3, 4. Okay. So we first start. The first step is to prove 1 implies 2. So the assumption that we make is X is compact. And our claim is that X is A, totally bounded, and B, complete. So we begin with the developing the proof for the first part of it, namely that compactness implies total boundedness. So this is what we are going to prove. So what do we have to prove? If you want to prove that, so we start with the assumption that X is compact. Okay? And now you want to prove that X is totally bounded. What does it mean? It means for any epsilon positive, you can find a finite collection of points x1, x2, etc., xn, such that the epsilon neighborhoods of these points give a cover for X. And for each epsilon, such a thing happens. Okay, so that's what we are going to establish. Okay. So let epsilon positive given. Then we know that B X epsilon X belonging to X forms an open cover X. Since X is compact, one can find a finite subcover. There exists x1, x2, xk, finitely many points. Of course, the points do depend on the epsilon that we have, and the number of points also depend on that. But what is significant is that is finitely many points such that psi epsilon is a subcover so corresponding to each epsilon there is a finite subcover for this neighborhood system. Okay? And this in turn implies being arbitrary exists totally. Thus, all compact metric spaces are totally compact. So that completes the proof of 2a. Now what we prove is that it's also complete. So the second part is once again we claim assume X compact and claim complete. That is, this means 1 implies 2b. Okay. So we already proved 2a that it is totally bounded. Now we want to prove that 2b is complete. What do we do? See, X is complete if every Cauchy sequence that is the limit of the sequence also belongs to X. So what we do, natural thing to do is start with a Cauchy sequence. So let then what we have is for any epsilon positive there exists n epsilon such that d of xn n epsilon. So this is the definition of a Cauchy sequence. Okay. So we have to show that the sequence xn converges to so that's our task. Now we use this fact that it's a Cauchy sequence. So for every k belonging to n, there exists nk such that d xn for every n greater than nk. This immediately follows from this assumption. Okay? Therefore, this is true for every k belonging to n. We choose the sequence nk such that so essentially we have picked a subsequence xnk of, so a subsequence xnk contained in xn, right? So this is a choice we have. Okay. Now we prove that xnk converges to some x, and consequently being a Cauchy sequence, xn being a Cauchy sequence, it follows that xn converges to the same x. Okay. So to prove this, we have to identify an x in some way. So what one does is this: let uk be defined as the set of all x belonging to x such that d of one by k. How does it come? Comes like this. So this is your x. You have a sequence like this. Now what happens is you are taking x and k here and then working out a 1 by k neighborhood of that, and then the complement of that. So you work out, see, uk complement is essentially one by k. What is this? See, this is close. Because d is a continuous function. Pick x and k, and this is a continuous function of x. Therefore, this particular set is a closed set because it is the inverse image of 1 by k is the inverse image of this closed bounded interval 0 to 1 by k, and therefore this is a using this continuous function, and therefore this is closed, which implies uk is open. And what is that? So you have x and k here. Take the 1 by k neighborhood of that. Take the open complement of that. Take the closed 1 by k neighborhood of that. And then take the complement of that. That complement is what you call, and uk is open. Okay. So you take the entire collection of uk and ask whether, so you take uk. Now what we observe is the following. Okay. You see that all the xn's for n greater than nk has the property that it is in this neighborhood. All xn okay. This is the one thing, that is the tail of the sequence. So essentially the tail of the sequence that we are considering, from some stage on, every element of the sequence is inside the complement of k. All elements for n greater than nk belong to closure. Okay, that is contained in this belongs to it, because we are talking about all elements. This is contained in what you call when this is a state of the collection uk. Now what we want to assert is that this does not provide, claim that for if it does, since X is compact, there exists a finite subcover. Say U1, UM. Okay. Now take, so what are the ADA associated with it? Now Xn does not belong to UK for every K, for every UK. So if you have U1, U2, UM, so if there exists such a finite collection, let 1 by Km so you have got, say, N1 associated with it, N2 associated with it, etc. Nm associated. Okay. So choose we use some number n equal to maximum of Nm. So Xn does not belong to UK for any K provided, see, we take this as small. This is the conclusion that we get. So what you are doing is we are trying to cover up X from and so on. We are going to cover up like this by the complements of this, complement of this, and so on. And so you see that always a tail is setting away from this, and the whole tail is contained in the particular ball. Okay, therefore you see that hence x is not equal to 1 to infinity which implies where x is and x belonging to x, but x does not belong to. Now we claim that x and k converges to x. Now what we have is that dx x and k is less than 1 by k. What does this mean? This means that since as a tends to infinity, it follows that converges to x, because this goes to 0 because d infinity. Now what we claim is that, of course, x and k is a subsequence of the Cauchy sequence xn. xn converging to now xn Cauchy implies xn sequence xn also converges to x. Okay. If the subsequence of a Cauchy sequence converges to x, then the whole sequence also converges to x. I mean, that's quite easy to. So the conclusion is that this is, we started with an arbitrary Cauchy sequence. Every Cauchy sequence is complete. So that's a completeness part. So we have proved 1 by 2. So that completes the proof of so we have proved this part. Now what we want to prove in the cyclic strategy, want to prove that 2 implies 3. That's the next stage, step 2. So we assume this. Assume totally bounded and complete. The claim every infinite subset of X has a so we set the notation, let E contained in X so what we want to prove is that E has a cluster point. Now let us work with the sequence 1 by n. Okay. So you know that E is totally bounded. As a subset of X. Because X is totally bounded, that means E is totally bounded. Therefore, for epsilon equal to 1 by n, there exists a finite subset Fn containing X such that union of X belonging to Fn contains E. So E is contained in this collection. And this is a finite union. Why? Fn is a finite set. Okay? Therefore, let us start working with this. This follows from the total boundaries. And it is true for every 1 by n. So, every 1 by n, there is a corresponding Fn, which is a finite set such that this relation we have a finite set. This is a finite unit. This is what we have just now observed. Now let us start working. Then what do we have? Then E is contained in union F1 B1. So there are finitely many sets Bx1 which provides a covering for E is an infinite set, and it is scattered over finitely many neighborhoods of say finitely many x's that belong to F1. So consequently, one of them if all of them have finitely many elements, what happens is it's a union of finite number of finite sets, which would mean the total number of elements would be finite. So E is already infinite, therefore this inequality or this containment relation does not. That's the reason. So one of them has to be. So let x1 is the element such that is infinite. Now run the same game. With E replaced by E intersection Bx1 and n equal to 2. Okay. Replacing E by F2 that is the balls of half radius with centers in F2, and F2 is a finite collection. Therefore, this further implies that E intersection x11 is infinite, now inductively choose a sequence xn where xn belongs to fn such that intersection such a set, such a xk exists or such an xn exists. Okay, so you have got now x1, x2, etc., xn, then you can take xn plus 1, etc. So you have a P xn such that this particular property is true. Above property works. What next? Now what we establish is this is a Cauchy sequence. Okay. Now note that E intersection one by n why it is so? Because you see that suppose n is greater than, then what we have is that E intersection E is a superset of 1 to n. That is 1 by n. This is true. But this is infinite. E is infinite. Which implies there exists an element so such an A exists. Therefore, what you can get then? Now we work out this one. So D is then less than or equal to D Now you see that this is less than 1 by m, and for n greater than m, we have two by n. So we use the completeness of this. Therefore, since X is complete, some X now we observe that dx xn is less than or equal to 2 by n. This is because for Therefore, limit we get dx xn limit m tending to infinity of dxm xn. Now what you see, this is so because the distance function is a continuous function. Therefore, you see that when you take the limit of this, so we have dx xn xn, which is what? Less than or equal to 2 by for every n. And therefore, it's a question. I mean, clearly, this xn converges to x. Now, note that dx 3 by n includes d 1 by n. That is quite clear because you know now already the distance between. So, see, if you take any element from here, you can show that this is so this is because can compute dxxn so you have dxn 1 by n is contained in x. We shall prove this. It's proved as follows. Taking a point from here, this is less than or equal to and this is less than 1 by n, therefore this is contained in this one. Okay. Now this includes infinitely many elements of it. Okay. Therefore, see, let us just briefly recall before we conclude the difference between a limit point and a according to the norm that we use in our base book by comparison. See, we say that suppose E is containing, we say that x belonging to x is a limit point of E if for every epsilon positive b x epsilon intersection is okay. Therefore, you see that there is no restriction that x should not be a point of E. Okay. So, if this contains only, and if x is a point of E, then if this contains only x, that's also a limit point. Okay. Therefore, every element of but there exists limit points there may exist x belonging to x not belonging to E as a limit. I will give a more example, a specific example to clarify this point. Suppose you take E to be equal to the open interval 0, 1. Then x belonging to is a limit point of E. Also 0, 1 not in E are limit points. Okay. So if you take the discrete metric space, take X, D, and E any subset of X, every point of and no point outside this is a limit point. In fact, if you take E to be it contains all limit points. And if you take E to be Q contained in R, all points in R Q. Now the point I wanted to make was that the B X epsilon may contain just X only from X. Then still it's a limit point. Now let us define what is a cluster and look at the difference of this two. It's far more efficient. What's a cluster point? Definition. Or accumulation. So let E if for every epsilon positive B X epsilon intersection contains one other than this is the important difference. We stop here when we define a limit point, but we stipulate a new condition that other than X, because X is always there. Okay. So that's the difference between the limit point and a cluster point. For example, you look at this one. The sequence containing with the usual logic. So E you take as the sequence order. Note that the only limit point of only cluster point of zero which does not belong to E, whereas all the points 1 by n union 0 are that's the difference. So that in a way highlights the difference between the two. Because if you take 1 by n, you can find a neighborhood. You take 1 by n, then you can have 1 by n plus 1 and 1 by minus 1. So you choose some epsilon which has the interval 1 by n minus epsilon to 1 by n plus epsilon. Lying between 1 by n plus 1, choose epsilon. Minus 1. You can find an epsilon this way. Okay. That contains 1 by n. Therefore, for any epsilon positive, this becomes 1 by n becomes a limit point. But then this cannot be a accumulation point. The reason is that it contains only 1 by n from this set. Okay. Right? Okay. Therefore, it cannot be a accumulation point. In fact, 0 has this property. No matter how small a neighborhood you choose, it will contain some point from E. Okay. So that clarifies the points there, namely accumulation point and the limit point, the difference between. That should be clearly understood. The terminology is important because in some books they do not distinguish between accumulation point and the limit point. So that one has to be careful about in what sense you are using this term. So here we clearly distinguish limit point and accumulation point. Okay, so we have proved that 2 implies 3. Now, what is to be proved is 3 implies 4 and 4 implies 1. We shall postpone this proof for tomorrow. Thank you very much.